Problem 2275, largest combination with bitwise AND greater than 0. So for this problem, I will first analyze the problem, then give a sort of brute force solution. Then I will explain some simplifications for this problem. So finally, you will find it's rather simple to absorb and solve the problem. So the bitwise add for an array numbers is the bitwise add of all integers in the numbers. So for example, you have number 1, 5, 3. Then the bitwise add is 1 and 5 and 3 equals 1. They also give another example, which is a single number. Of course, the bitwise add is itself. So notice that the bitwise AND is an associative operation. So here we are given an array of positive integers called candidates. So we would like to evaluate the bitwise AND of every combination of numbers of candidates. So each number in candidates may only be used once in each combination. So in other words, a number either appears or not appears, not in the combination. So we are required to return the size of the largest combination of candidates with a bitwise add greater than 0. So in other words, it's non-zero. So here is an example. For this example, the output is 4. So this 4 numbers has bitwise 16, which is greater than 0. So we can check as the problem said. So any combination with a size greater than 4 will result a bitwise add, which is 0. So similarly, example 2. So this actually has some reasoning here. So the output is 2, which is the length of the candidate, because the length the candidate contains only one number if we regard it as a set. So for bitwise add, and a number itself, add itself, still result itself. So here the constraint is that the candidate length is up to an order 10 to the power 5th. So in other words, if we want to solve the problem in a brute force fashion, so it's not going to pass the time check. So the second constraint is about the candidate element itself. So let's first give an easier example. Then we want to analyze how we approach that. We will first give a sort of longer solution, which is more brute force, but it means to understand the finer details. And then we simplify. Essentially, we can write it in one line, but writing it in one line is not our goal. So we want to achieve a easy to understand solution, and we want to gain more readability. So first, let's examine an example. For example, if we are given candidates like 1, 7, 8, and 9. So in order to check the bitwise add, we want to change these 4 numbers into their corresponding binary representation. For example, 1 corresponds to 0001. I would use 4 bits here. So 7, so it changed to 0, 1, 1, 1, right? So it's 2 to the power 2 plus 2 to the power 1 plus 2 to the power 0 is 7. So similarly, 8, it has a binary representation which is 1, 0, 0, 0, because 1 to the power 3 is 8. So again, 9 has a binary representation adding 1 to 8 is 1, 0, 0, 1, right? So in order to have a largest largest collection of numbers with which result a bitwise add is non-zero or greater than 0. So we can check each of the corresponding bit positions. For example, here, if we check this bit positions corresponding to 0, 0, 1, 1, then if we choose a number 8 and a number 9, we will get something like this: 8 and 9 equals this bit is 1 anyway. We don't care about other bits, so this is non-zero already. So in this case, we get a collection of these two, right? So similarly, we can check this position, the 0, 1, 0, 0. So if we look at this position, we can only choose 7, right? 7, is corresponding to 0, 1, 1, 1, of course, but the collection has less 1. So now if we look at this bit position, we have 0, 1, 0, 0. Again, we can only consider 7. Otherwise, if we include other zeros, this bit position is non-zero, right? So we get this collection is 1. So now if we look at this bit, last bit, so we have 1, 1, 0, 0. Then if we choose 1, 7, and 9, so their bitwise add equals something like star, 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 1. So because this last bit is already 1, so the result will be greater than 0. So from this example, actually, we can get the main idea. So the main idea is to check the binary representations of the elements in this candidate. Then we count the corresponding bit. We see which corresponding position corresponding to most non-zero bits. So then we choose that corresponding numbers. Then we get the largest collection, because as long as the one specific bit position, all the numbers are non-zero, then the bitwise add will result in non-zero or greater than 0 result. So that's the main idea. In other words, check each bit position and find how many non-zero bit in this position, in this corresponding position. So with this idea fixed, let's write a code corresponding to this solution. So this way, in some sense, is brute force, but we want to do it first, then we check other simplifications. So as a first step, so I want to do a binary representation. And before that, let me do some estimate. So here, the problem says that each candidate is bounded by 10 to the power 7. So yeah, if you look at this, check their binary positions, so we can check how many bits we need. So we can check logarithm 2 of 10 to the power 7. So which is 7 times log 2 of 10, right? So which is less than 7 times log 2, 16, right? So this log 2, 16 is 4. So we have 7 times 4, which is 28. In other words, 28 bits will be sufficient. So now for this solution, let me, as a step 1, so I will do I will check binary representation, right? So though we can do it use some ready to go function, but here we want to do it from scratch. So we see to binary. So here we consider a number. So Then we will initialize a result which is empty. So we want, so the order actually for you put the last bit in the head of the list result or behind, it doesn't matter as long as you make the positions aligned. So we will do a simple while loop, which is routine. So while n is greater than 0, so we want to check the quotient and the remainder. So here we use the mood. So with respect to 2, because we are using binary conversion, binary representation. So the result will append this r, which is either 0 or 1, and then we update this n to the quotient. So finally, due to our estimate, let's fix it as 28 bits. So we will return something like this result plus. If there are not enough, so we will align using 28 bits. So we want to do something like this: 28 minus the length of the result. So this way we get the binary representation of each number. Then we want to compare each bit. So first, let's get the binary representation. So step 2, to binary. So let's use an array, initialize an array. So then we iterate from candidates. So for y in candidates, so we append this array the corresponding binary representation of this y, right? So now let's do step 3. Step 3 is count corresponding bit positions. So here we are going to use a function called zip. So first, let's initialize a result, which we are going to return its final state after our scan. So then for this it in zip star array. So this star array is corresponding to a transpose of this, if you regard it as a matrix. So it's corresponding to this one, and this one, and this one, this column. So then we want to count the non-zero bit. So the result will be updated like this: maximum, the result, and the sum of it. In other words, the sum is the number of 1 bits in this position, each of the position. Then we will return the result. So let's do a quick check. So it passed the special case, and also it passed the general case, I guess. So now we know the basic idea. So now let's write in a more bit operation fashion. So let's call this solution solution V1. Now let's look at another solution. So in this solution, basically we know due to our estimate, we just need to check the 28 bits and then count each of the corresponding non-zero 1 bits. Then we return the maximum. So for this we can write like this. So we will return directly. We can use because the max function can be passed a iterator. So we will check if the ith position has non-zero bits and what's their sum. So we'll sum. So in order to check ith bit, we can do something like this. We will left shift this 1 by I bit positions, and then we check this with respect to a. If this is greater than 0, so it means this will have a non-zero bit for a in candidates. So here, because we need to check all the 28 bits, so for I in range 28. So this basically is a condensation of the above solutions. So let's do a quick check. So it passes. So candidates. So it passes this special case, and also it passes the general case, I guess. So this is the one way of writing. So actually, we can do slightly more clean, in a more clean way. So we can do something like this. So let's call it. So we want to check something like this. So we will write like return max same as, but we change a little bit about the check. So we in order to check the ith bit, so we shift to the right about A and check with 1, right? We will check. We will examine if the ith bit of A, where A is an element in the candidate, is 1 bit or not. So for A in candidates, then we just check all the bits. Range 28. So again, 28 comes from the constraint on the candidate, which is less or equal than 10 to the power 7. Then let's check this solution. So we run this for the special case, and then we run it for the general case. So it passes the check. So yeah, so basically this is the solution, a solution to this problem. So we first went over a brute force solution, and then we give 2 simplifications. That's it. Thank you very much.